In the previous module, I showed you the one predictor linear regression model, and I also showed you the types of tests we can perform using our linear regression model. Let's see how we can fit the regression line in JMP and where we can find each of our parameter estimates and the tests of those parameters. We actually have two different platforms we can use in JMP. The first is using FitY by X, and the second is using FitModel. Let's start by using FitY by X for these data. Now let's first specify hours, that is, the thing we're making a prediction from, as the x or the factor. Next, we'll specify grade as our response. You'll notice that FitY by X automatically detects this to be a bivariate fit, that is, one quantitative variable predicted by another quantitative variable. When I click OK, JMP will return the simple scatter plot of these points, and to fit a line, we'll go to the red triangle and select Fit Line. What JMP will fit is the linear regression of grade onto hours. And we're even given the prediction expression. You'll recognize these numbers from what I showed you in the previous modules. So this line is saying that grade is equal to 72.37 plus 1.77 times hours. That is, the line starts at 0 at 72.37, the amount of grade somebody is predicted to have if they have 0 of x, and we're adding 1.77 units of grade for every additional hour of study. Now let's look through the rest of our output. Notice first the summary of fit table. So R square here you may recognize from before. R square is the proportion of variance that this model accounts for in Y. It's literally the proportion of variability, the proportion of variance in grade that can be predicted on the basis of hours. And in this case, this model is predicting most of the variability in Y. That is, on the basis of the number of hours somebody studies, we're explaining almost 97% of the variance in Y. Now let's look down a little bit further. We have the analysis of variance table, and in this case, the analysis of variance table is reporting the p-value for testing the slope in this model. Now I want you to notice the different sources here. So the source of model has 1 degree of freedom. That 1 degree of freedom is the slope in the model. And the model, or the sums of squares regression, are reported right here at 219.65. Now, the mean square for regression, 219.657. Notice that this is the same as the sums of squares since we only have 1 degree of freedom. Remember, a mean square is simply the sums of squares divided by the degrees of freedom for that parameter. So, in this case, we have a mean square exactly equal to the sums of squares, which gives us the F ratio. So the mean square for the model, or the mean square for regression, divided by the mean square for error. Notice the mean square for error has 4 degrees of freedom. This data set has 6 individuals, and we used up 1 degree of freedom for the slope and 1 degree of freedom for estimating the intercept. So we have 4 degrees of freedom left for error. So the sums of squares, 6.34, divided by 4, gives us the mean square for error, our best unbiased guess of the variance in the population around this line. So this p-value here, our test of this model, is really a test of the slope. The analysis of variance table is not testing the intercept. In essence, our ANOVA here is simply a test of the regression relationship, independent of where the regression line starts. Finally, the parameter estimates table gives us our t-tests. Now these were the first types of tests I showed you that are formed in the basic way we form all t-tests. The actual sample estimate minus what is expected under the null hypothesis for that parameter divided by the estimated standard error. So our first test, our test of the intercept, is we have the actual estimate here, the intercept in the model, 72.37, where this line hits the y-axis. We have the standard error, and I actually showed you the formula for that. The t-ratio that we form, taking this estimate divided by the standard error, and then our p-value that is looked up from a t-distribution. Our next line is the parameter of the slope. So our slope in this model was 1.77. For every additional hour of study, we're adding 1.77 hours to the grade a student is expected to get. Next to our estimate, we have the estimated standard error, 0.15. Now before I go on, notice that the estimated standard error for the slope is substantially smaller than the estimated standard error for the intercept. You might recall when we looked at the formulas for the standard errors that our formula for the intercept, that is the estimated standard error of that coefficient, had a lot more terms in it. And I gave you the insight that there's simply more things that can go wrong in estimating the intercept. So this term in our model simply experiences more error, and that's reflected in the standard error. Alright, so for our hours, our slope in the model, we have our estimated standard error, and we have a t-ratio that's formed by the estimate, 1.77, divided by that estimated standard error, so 11.77. And this gives us our p-value for testing that slope. Again, you'll notice 0.0003 is the same as our analysis of variance p-value. These are testing the same things. So the parameter estimates table is using t-tests and the t-distribution to form those tests, and the analysis of variance is forming that test on the basis of the partitioning of the sums of squares total. So we have some total variability in y, 226, and that's partitioned into two components. Sums of squares due to regression, that is due to the slope of the line, and sums of squares due to error, that is error around the line. So in either of these, we're getting the same value. That is, the p-value from either of these tests, either the ANOVA or the t-test, are always going to match when we're doing simple linear regression. Now, which one you use is really up to you. They're testing the same thing, so depending on in which context you're reporting your results, it might make more sense to report an F, and sometimes it may make more sense to report a T. So you'll often notice if you're talking about regression, people will actually expect a t-test of that parameter. It's equally right to give the F ratio, but just note that people will be probably expecting the T ratio. Now let me scroll back out, and I want to show you a couple other options that are available under the red triangle for linear fit. So let me click on this. Now first, we can get confidence intervals on this line for the fit and for the individual. Let me put on the confidence curves for the fit, and notice what this draws around the line. It's actually known as a working Hotelling confidence band, and this is really a confidence interval around the line itself. Where do we think that line really is in the population? We can also put on a confidence curve for where we think individuals lie in the population. Notice that that confidence interval is wider because where this line is in the population, remember, represents the conditional means of y given x. Whereas the confidence band for where individuals are, well, that's actually a representation of the error around the line as well. Where do we think individuals will fall in the population if we were to get a new individual? So if we were to take a new person in the population who studied 6 hours, our best guess of where that person would lie would be between those outer lines. Let's look at some of the other options. We can also shade these, and if you're actually producing these and printing them out, I would recommend shading them. It actually looks a lot nicer, and I think gives a nicer view of the actual uncertainty. Also under here, you can save the predicted values from our model. This will actually save what is predicted for each individual to your data table. Let me do that and show you what that looks like. So if I scroll across here, notice for each individual, let's take Tom. What was predicted for Tom was a score of 91.85. And notice that that is really the point on the line at 11 hours of study. So this is just printing out what the line predicts. Literally, if you were to type this equation into a calculator and substitute for hours, 11. Now under the red triangle, you can also get the saved residuals. So we can save these directly to the table, just like the predicted scores. What this will save is the deviation between each individual's actual score and what was predicted for the individual. Notice for Tom, the model over-predicted him by 0.85. So 91 minus 91.85 is negative 0.85. So the residuals that we save allow us to actually look at the residuals in a little bit more of a detailed way. It's often the case that we'll want to interpret or work through these residuals, maybe using the distribution platform or another platform, to see if they obey our assumptions. So we always assume something about the residuals. They have in the population a normal distribution and equal variance across the line. So we'll come back to those assumptions at a later point, but notice that you can save the residuals simply by doing it under the red triangle.